We've talked a fair bit about what missing values are and visited some basic techniques to fill in those missing values. In this video, we'll revisit those basic techniques and see some of the advanced methods to fill up missing values. By the end, you'll have a basic tool set for creating complete data sets. Filling in missing values is also sometimes referred to as data imputation, because you impose a value on the data point based on characteristics of related points. Of course, data you encounter in the real world often has missing values, and data can be missing for various reasons. The first type of missing data is called missing completely at random, or MCAR. MCAR happens when there's no connection whatsoever between the observed data and the missing data. For example, think of a survey that's been filled in by a group of respondents. If there's a small set of missing values due to human entry error or an internet glitch losing some results, files being corrupted, we could say that the data is missing completely at random, and there's no correlation between those missing values and the observed data. Then the only thing that matters is some percentage of your data is missing. You can throw out those incomplete examples and it won't change your resulting model. Unfortunately, it's uncommon for there to be no relation at all between missing values and observed values. The second type of missing data is missing at random, just at random, not completely at random. Sometimes we're not as clear naming things as we should be. So missing at random means there's still some randomness in what values are missing, but it relates to the data you actually do have. There's some systematic difference, and the missing values are influenced by something else present in the data. Something in the data you do have correlates with the values that are missing, so if you simply throw away the incomplete data, you're changing the distribution of your training data, maybe in some important way. For example, if we're doing a survey about this specialization, and one of the questions is how many courses you've completed, and another is how well the assessment questions tested your knowledge, you might find that 90% of respondents who've completed all 4 courses in the specialization have responded to that second one, and yet only 60% of respondents who have completed 1 out of 4 courses have responded. There's a real possibility that the experiences of these 2 groups are different. We're hearing much more from people who completed all 4 courses. Their opinion of the quality of the assessments is overall likely to be different than the people who didn't complete all of the courses. We can say that the missing value has some conditional dependence on one of the other features. The third type is called missing not at random. This is the trickiest case. It means there's a consistent reason why that particular data is missing, and it's directly related to the value itself. This comes up in surveys when there's some question a person might not want to answer because of the answer. If you have a survey that includes gender and you simply ignore all the respondents that choose not to answer, you're likely to severely bias your results. Or imagine the case of clinical assessments. Maybe some of the data is missing just because the patient forgot about the appointment. Or maybe they died. Those are very different cases. These missing values are the most difficult to fill in because they hold important information that you can't necessarily recover from the data you have. Algorithms that use such data need to accommodate missing values as part of the process. So let's set aside that trickiest case and look at what techniques we can use for filling in values that are missing at random or completely at random. Let's start with the most simple use of data imputation, imputation by constant. That means that all of the missing values of a feature will be filled in with the same value, and it won't be dependent on any other feature. One of the easiest ways to do this is to make all missing values in a feature 0, or some constant value chosen another way. You can also choose a value based on the observed values of the feature. One most commonly used way is using the mean of the observed data to be the missing value. This can be sensible, but watch out for cases where you might find that the mean is skewed because of a few very large values. If that happens, you might want to use the median of the observed values, or you could similarly use the most frequently occurring value of that feature. But now let's make this imputation a little bit more interesting by using multiple values for imputation instead of always inserting the same value. It might not be helpful to just have random imputation. What if instead of a mean value on all the values of a feature, we use mean values pertaining to a specific value of another feature? For example, if we want to fill in some missing values of age, we can use the gender feature to compute the mean values separately and fill them up accordingly. Or for a survey example, we calculate the average value separately for the 2 groups, those who completed all courses and those who completed only 1. So why not take that further and use all the features that we have to fill in the missing values? We can do that, and we can use some of the machine learning algorithms that you've already seen in course 2. We'll see a couple of them in this video, but they're not the only ones we can use. Let's start with how we use k-nearest neighbors to fill in the missing values. From our previous example, if we need to fill in the height value, we can use a distance metric, and using any number of other features, in this case, let's say we only take the age, we can find the nearest neighbor of the data point whose value is to be filled, and fill it in based on the value of the neighbor. If more than one neighbor is considered, you can take either a mean of the values of the neighbors or a weighted mean based on the distance of the neighbor for continuous values, or take the most frequent for categorical features. You can also use regression to impute values. You use a regression model based on the observed features and then predict the value for the unobserved feature. The predicted value is now what we use to fill in the missing numbers. This method of using regression models and using the exact value of the prediction is known as deterministic regression imputation. A variation of this is to add a small random value to the predicted value and use that to replace the missing value. This is then known as stochastic regression imputation. We've seen methods that can be applied to IID data, but what if the data instances are correlated? Luckily, we have methods we can use for interdependent data as well. Let's take the example of temporal data, where the value of each data point is related to the value of previous data points. For some applications, you can make an assumption that the values might remain the same or closer to the value that's been recorded the last. In that case, we can use the last value and fill in the missing values until there's another observed occurrence, and this is called forward fill. Or sometimes we want to use the future value to fill back the previous values. In that case, we're doing backfill. In some cases of temporal data, the domain might allow us to make assumptions that a specific feature is going to be increasing or decreasing. For example, if we have a temperature reading for each minute and we have 5 minutes of missing values, there's a good chance that the temperature reading for those missing minutes could just have been increasing or decreasing regularly. In these cases, we can use linear interpolation, where we fill in the missing values by drawing a line that connects the last observed value to the next observed value, and the values of the missing time steps are drawn from that line. What method you use to fill in missing values depends on the reasons the data is missing, as well as the characteristics of the data itself. Often how you do the data imputation has a significant effect on the performance of your model. So you're faced with the usual mix of knowing your data, understanding your domain, and carefully paying attention to how your learning data relates to your operational data. Other methods exist, and of course this is yet another active area of research, but now you have a good idea of basic techniques and considerations, and you're ready to create a complete data set.